again, thank you all for the invitation and also this whole initiative. It's a very important initiative in my opinion. So thank you very much. I'm also delighted to see Frank and Alios, who I also met a long time ago in France. I don't know whether he remembers in Portugal Islands, where we had a very nice kind of a meeting organized by Guillaume Buffon on the first meeting a long time ago. And I'm delighted to see Deepta also in the audience and Shubhashish, of course. Thank you for the invitation. Now, so in the next 15 minutes or so, I'm going to briefly kind of discuss about some of the research activities in my laboratory, especially from a viewpoint of emergent dynamics in colloids, which actually has a strong motivation thanks to a lot of interesting work which has been already done by various people, especially Frank's group and also many other groups. I hope I actually can also present something which has some kind of peripheral connection, but also some motivations from a lot of work going on among the people who are already doing work in this particular area. So my own research activities can actually be roughly divided into four parts in my own group. We look at also specifically the Brownian dynamics in an optical trap, where we are interested in trapping single nano objects and looking at the Brownian dynamics of the trapped object as a function of space and time. We also do spectroscopy in such kind of situation where we trap objects in such small situations. Of interest to this particular talk is the assembly and some kind of pattern formation, where we look at some kind of structured light interacting with certain kind of colloidal matter, and how do they assemble, how does it evolve as a function of space and time. That is something I'm going to discuss. We also have been working on optothermal gradients. For example, you can actually excite the wire at one end and you can pull the particle along this particular wire, and you can play around and do a lot of interesting things. And the fourth component, which I'm not going to talk again, is something related to measurement of optical momentum. You will see also a lot of stuff done by one of my former PhD student and current postdoc of Frank, Deepta, who played a very critical role in this particular project. And there are a lot of peripheral connections also to the work, what has been done by him in this particular presentation. So this is kind of roughly the activities in my group. But what is of interest to this particular seminar is to look at the general aspect of spatiotemporal kind of confinement. Essentially, if you look at the way matter is kind of arranged as a function of space, it goes all the way from molecules to planetary systems. And along the y-axis is shown the kind of confinement you can actually achieve. Most of the matter, what we kind of perceive within the visible wavelengths and or in any particular part of the electromagnetic radiation, falls into some kind of interaction in this particular regime. So you would also see that there are various different ways in which you can look at confinement. And due to this particular confinement, very interesting dynamic structures evolve as a function of space and time. But what is of interest to us is also to look at the dynamic structures which can evolve due to such confinement, and you can obtain some new function out of it. So one of the interesting functions what I'm interested in is the optical function. For example, you can achieve some very interesting optical states by confining soft matter in such a kind of system. And the kind of confinement what we are now discussing in this particular talk is to do with something like a soft confinement per se, where you essentially are using some kind of an optical or optothermal potential to confine objects of interest as a function of space and time, and ask what is the kind of evolutionary structures you can obtain from such kind of a confinement. And that is something which is pertinent to this particular talk. This all has a very strong motivation from a beautiful piece of work in collaboration with Frank Chico's and Klaus Kroy's work on hot Brownian motion, where one is interested in looking at objects which are heated. And per se, the conventional Brownian motion, what we know actually has to be altered a little bit with a kind of a specific kind of diffusion constant, which is scaled with respect to the new temperature and the new viscosity. And these scaling factors is something which few speakers have also spoken in the past. There is a very interesting question of how to understand hot Brownian motion in certain kind of environments. What is the kind of structures you can have as a function of space and time when you confine them in an optical trap? And these are the questions of interest to my own group. There's also a lot of interesting work which is going on in various different groups across the world. I would urge audience to actually also have a look at this particular piece of work from various different groups. So of interest to us is to understand how do these hot Brownian colloids behave. For example, you take light and you have light absorbing colloids. One of the crucial elements you would be interested in is to understand the interaction between the light and the matter. And this is essentially given by the power which is either scattered or absorbed. And this is again dependent on the incident electromagnetic radiation. And also there is a crucial element of scattering and absorption cross section. If you look at from a light matter viewpoint, you can now look at this particular interaction from a heat power density. So if you now look at the imaginary part of the colloid, whatever you're interested in, and that imaginary part of the colloid now interacts with the intensity of the light, which is incident. And of course, there is a frequency dependence. And if you take this particular heat power density and integrate over the volume of interest of whatever colloid you're using, you end up getting this total power absorbed. And this total power absorbed is again connected to this particular formula, what has been already mentioned. And this is very well appreciated fact that you can heat objects using external electromagnetic radiation, and that can be used for various different applications per se. Now, what is of crucial interest is to generate some kind of forces and torques using such kind of external electromagnetic radiation coupled to imaginary part of the dielectric constant. So one of the things what we have been studying extensively in my lab is to understand evolutionary dynamics of nanoparticles infused colloids. Essentially, we are interested in the motion under confinement, and the kind of colloids what we study is of this kind. For example, in this particular view graph, what you're seeing is a polystyrene colloid which is infused with iron oxide material, which very strongly absorbs light at visible frequency. Once you actually have such kind of highly absorbing colloids, there are some very interesting dynamic states what one can generate. And the questions what we then ask is, how do thermally active colloids, such as the one which I showed, interact with structured optical potentials? And how does this evolution change for active passive mixtures? And what are the new kind of dynamic states one can achieve? So let me jump into one of the first piece of work what I'm going to discuss. In this particular experiment, what we were interested in is looking at the evolution of such kind of active colloidal matter in certain kind of structured light. So one of the simplest structured light what you can generate is to defocus a laser trap so that you now have a distribution of intensity in such kind of a laser trap. And then you ask, how does these colloids interact with this kind of defocused laser trap? What are the new evolutionary states what you can achieve in such kind of matter? So let me first illustrate with a comparison between the active and a passive kind of colloid. In the passive colloid, we essentially are looking at 1 micron polystyrene colloids. In the active colloid, which is a thermally active colloid, you essentially have polystyrene colloids infused with the iron oxide material. So let me just show you the comparative kind of situations. Now, what you're seeing here is conventional hexagonal formation of colloids in a defocused laser trap. So you see this beautiful hexagon forming in this particular trap, and this is the kind of structure you obtain. Now contrast that to a situation where you have this thermally active colloids. You now have some very interesting situation where there is a short range repulsion and a long range attraction between the colloids. So this creates some very interesting situation where you would now have evolution of these colloids in this particular pattern formation, and this leads to some interesting dynamic states. So in order to understand why these kind of structures actually evolve, we further look at these kind of states. Okay, 1 second. Let me go back to the. Oh no. Can you see my screen yet?
Yes, we see this presentation still. I mean, if you mean that.
Oh, yeah. But I think you see a kind of a hazy screen now.
Yes.
Now it's back. Okay, no problem. Okay, now if you look at this, this same colloids, and if you ask what is the kind of interaction you have, there is some kind of a short range repulsion. For example, if you increase the power of this laser which is creating this trap, you gradually see that the colloid actually uh, kind of emerges out of this particular region of high intensity. And if you now decrease the power, the colloid tends to actually come to the center of this particular trap. Now contrast this also to some very interesting polarization states. For example, if you now have this trap formed with Y polarized kind of light, and you switch the polarization to X polarization, you will be able to switch the orientation of this particular kind of dynamic trap, whatever you are now seeing. So you can also now study these kind of colloids from the viewpoint of trapping and tracking. So you can now perform experiments where you look at the kind of temperature distributions in such kind of situations. We use a technique which is kind of also pioneered by Frank's group, where one can use liquid crystals and illuminate the colloid of interest, and you essentially get a very beautiful circle of this kind. Because of the phase transition of the liquid crystal, you would be able to now look at the radius of the liquid, this particular circle, and estimate the temperatures what you can get. So we do all these kind of analysis with respect to the trap, what we have achieved. For example, we also show that as a function of power, you can now tune the precise distance of this particular object of interest. You can also look at the temperature distribution in such kind of situations, and also kind of a trap stiffness with respect to the polarization states, what one can achieve. So one can take this particular kind of thinking logically into a slightly new direction. One can ask, can we also study emergence of certain kind of optical processes? In this particular case, emergence of directional rotation in an optothermally activated colloidal system. So in this particular case, of interest to us is to understand the directional rotation which can emerge. So I'm going to play a movie where you'll see that the colloids are now mixed. In this particular case, before I go into the details, the larger colloids are passive colloids. The smaller colloid is the light absorbing colloid. So we created an optical trap at the region of interest in this particular situation. And we now look at the rotation which emerges out of this situation. And you can see, depending upon where the active colloid is placed in this particular trap, you would either get the counterclockwise rotation or the clockwise rotation. So this precisely depends on the detail of the particle of interest, what you are now looking at, and it has some very interesting ramification. One of the interesting ramification is that you can show that by switching the position of this particular laser trap with respect to the active colloid, which is a thermally active colloid, you actually can switch the rotation direction. So I will illustrate that. So as you can see, there is now a rotation which is undergoing motion in the counterclockwise direction. And you will see in a few seconds that we're going to shift the position of this particular optical trap onto the other colloid of interest. And in seconds, you will see what happens. Now we switch the spot, and you see that the rotation moves from clockwise, anti-clockwise to the clockwise rotation. So what is this telling us is that you can now create directional rotation by placing your optothermal potentials at a specific location with respect to the light absorbing colloid. And you can now play around and create a library of very interesting structures. For example, you can now ask what is the criteria for the emergence of rotation in such kind of experiments. In this particular case, you can see there are two passive colloids, one active and one passive colloid, or three passive colloids. You end up with a non-rotating state. Whereas the moment you have two passive and one active colloid, you see that the rotation emerges. So as you can observe, there is only just the conventional Brownian motion in all these three situations. Whereas the moment you have this kind of combination, you induce rotation in such kind of states. This important conclusion, what one can draw is that the combination of the colloids play a critical role. In addition to that, the symmetry of the colloids through which you can place them in this particular trap also matters. So in this particular situation, you will see there is a structural asymmetry in this particular colloidal formation. Whereas the moment you take an achiral state, you would end up getting a non-rotating kind of a state. So you will see there's a chiral motion which is associated with the chirality of the structure itself in the two dimensions. Whereas if you have a symmetric kind of structure, you end up without any specific non-rotating states in such kind of systems. So one can now play around with these things. I would urge you to just have a look at some of the details in some of the articles what I have written, especially in the context of also looking at the light scattering from such kind of a colloids. If somebody is interested, I would urge you to have a look at this. And also, you can take the same thought process to ask what happens to plasmonic colloids when you place them in special kind of structured light. In this particular case, optical vortices and other kind of systems. In this particular review, I've detailed all the foundational issues and also some basic elements of such kind of interactions. If somebody is interested, I would urge you to have a look at it. So I would kind of conclude my talk by acknowledging many of the people who have worked in my group. Specifically, Deepta was the one who initiated a lot of interesting questions related to some of the trapping techniques what I showed. Sunny also played a critical role in establishing nanoparticle trapping kind of techniques. And also Rohit, who is now in Birmingham as a faculty member, also have played a very critical role. And of course, Rahul played a very critical role, taking the baton from Deepta, and all my present group members are also working on various different things. I also thank my colleagues, Vijay, Apratim, and Deepak. They have been very instrumental in motivating interesting questions. And my funding comes from various institutions across India, and also from some places in India, and also in the past from Indo-French and Indo-US grants. Finally, I would urge students, if some student is interested, you can also look up some of the stuff what I write in my blogs. There's a lot of details there. You cannot cover everything within my thing. I also do podcasting where I am interested in kind of humanizing science. And as Frank mentioned, I'm very deeply interested in history of science. So if somebody is interested, I would urge you to look into it. And finally, and the most important thing is, thank you all for your kind attention, and also this wonderful platform for doing this wonderful kind of series of lectures. Thank you very much. Thank you.
So thank you very much, Pavan, for the interesting talk and the results on the rotating colloid. So I have already one question because Michel raised his hands. So Michel,
yes, thanks a lot. Thanks very much for this very exciting lecture. I was very fascinated. I was wondering the case of the magnetite, or magnetic iron oxide nanoparticles, doped nanoparticles. They are magnetic. So have you tried to look at the interplay between all these forces created by temperature gradients and the magnetic forces? I guess that would be a very interesting phenomenon.
Yeah. Thank you very much for asking this question. In fact, our logical kind of progression is towards also inducing an external magnetic field. So what we have now studied on purpose is not to induce any external magnetic field, so that we know how does it behave in an optical regime. Now, what we'll do is take the same kind of situation and apply a weak magnetic field or a pulsed magnetic field or any specific kind of external magnetic fields, and also look at the dynamics. So we are working towards that particular direction. And I should mention, since it was asked, that we've also done similar kind of trapping experiments, albeit with slightly smaller particles like fluorescent nanodiamonds, which are also very sensitive to external magnetic fields. So one can also look at effect of external magnetic fields using such small colloids, as small as a few hundreds of nanometers. But in this case, as absolutely correctly identified, we can also induce an external magnetic field. And we have observed some interesting effect, but we are yet to really establish the whole protocol of how to go about performing this experiment. And this is something which is underway. Yeah. Thank you very much for the question.
Okay. Thank you very much. So we have to stay tuned. Thanks.
Yeah.
Other questions? If not, then I can ask first. So what is really then microscopically setting the direction of rotation in the direction of the heated particle in these trimers you showed at the end, or the structures. So what's the detail of the process?
Yeah. That thanks for asking, because there's limited time. I could not go into detail. One of the crucial elements is, if you look at the kind of distribution of temperatures in such kind of systems, one actually has two different forces. One is the optical force, which is essentially confining them and creating a long range attraction. And there's a short range repulsion, which is coming from the local gradient of temperatures, which you create. So if you look at these kind of distribution of temperatures and the relative position of the light with respect to the colloid, this induces some kind of a force which is tangential to the particle in this case. So depending upon where you're placing your trap's center, there is now a kind of a directionality associated with the rotation, angular momentum, so to speak, because a particle cannot escape, neither can it be static. So therefore, it has to somehow conserve the angular momentum. And the angular momentum conservation requires that it has to move in a particular direction, either in the left or the right direction, depending upon in which particular platform. For example, if you observe here, the colloid actually takes the lead. The colloid takes the lead in both the directions, so that wherever now there is a gradient of heat created, it can neither be escaping out of the trap, nor it can be static in this particular region. And therefore, it has to rotate. And that rotation direction is determined by the gradient of the temperature, what you now create in such kind of situations.
Yeah. Okay. So is there in any case, so if you just have a central passive particle and the heated particle, and is there also maybe any influence of the inhomogeneities of the particle with respect to the heat sources that are distributed there?
Yeah, it's an important question. We also tried the experiment with a diver of colloid, where you have one active and one passive. We do not observe the rotation.
Okay.
In fact, if you look at this one active and one passive, the second situation, that's exactly what we are trying to do.
Yeah.
So you don't observe the rotation in this situation. So there is some kind of symmetry also associated with the colloids, because this essentially is now like a Janus particle, if you look at it. So essentially, this kind of associates itself as a kind of a distribution of temperature, which is asymmetric. And you do not observe the rotation in this situation. And we have consistently been observing this for a while, and we do not observe the rotation for this situation. Whereas if you now break the symmetry in a particular way, as shown in this situation or in these situations, so you induce the rotation only when you have structural symmetry and also a temperature kind of distribution. So it's a combination of effects. To be very frank, these are details which I'm telling, which is sufficient to just explain this. The real actual details of the distribution of temperatures is still, because we are also not considering anything hydrodynamic in nature. But surely there is surely some kind of an effect due to hydrodynamics too. Therefore, I would be very cautious in mentioning that this is the kind of explanation we have currently. But there is a lot more to the story than what I'm just mentioning.
Okay. I see. So Yuping is ready to ask as well.
Yes. Yeah.
Thanks.
Thank you, Frank. Hi, Pavan, very exciting work.
Thank you, Vin. Yeah.
So I'm wondering, just follow Frank's comment here. Can you comment on the rotation rate and the stability of this cluster? How that depends on the power or other parameters?
Yes. In fact, we have actually a detailed kind of a study where we also measure as a function of power this whole kind of situation. So you would be able to now rotate these objects up to powers of as much as 20 milliwatt per micrometer square. We have gone even beyond that particular number. And this rotational speeds actually can be increased by increasing the power of the laser beam. That is point number one. The stability of these clusters, for example, the first situation where you do not have the rotation, the stability is that you end up getting symmetric kind of distribution up to number 8 or number 9 of colloids. Going beyond that, it creates a kind of an unstable situation. For the rotation, the number of colloids what we have trapped is roughly about the numbers what we are showing in this particular, for example, in this particular situation, it's 4. We have also trapped a few more, maybe roughly about 6 or so, but the stability slowly starts reducing in such kind of colloids. But the relative stability of the colloids of less than 6 is reasonably good in such kind of traps. And most of the time, we are very cautious of performing this experiment in quasi two-dimensional kind of situation, which means that if you observe the design of our traps are mainly in this way. We bring the laser beam and have a tightly focused beam from the top, and then we do all our imaging from the bottom. So we essentially do the trapping at the surface of this particular kind of chamber, whatever we now create. And most of the traps what I have discussed in these studies are all two-dimensional in nature. So we don't do it in the third dimension. So there is now kind of a scattering force which is ensuring that the particles are all at the 2 dimensions. And that's the reason why you will see the assembly is also reasonably well resolved in such kind of systems. So yeah, the parameters of power and the number are crucial. It's a very critical number, a critical parameter. We've also done a detailed study in the second one too. In the first one too, in the first paper too, we have actually discussed about this particular issue. So there are a lot more details in this particular work. I would urge to have a look at it. Yeah.
I see. Thank you. Very exciting.
Thank you. Thank you.
Okay, so you accidentally already answered also the question in the chat of Falco. So this is done as well. Is there any kind of additional question? Because we have 1 minute to go. So if there's now an urgent question.
Yeah, Falco is asking how big is your chamber?
Yeah.
Are the particles confined in quantity? Yeah, the answer I just answered the same.
You just answered, so perfect.